Hi, this is Ayush and today I'll be talking about symmetries in quantum mechanics. We must have come across conservation laws at some point of our life. Did we ever give a thought why do they exist? Is there a underlying principle behind them? Precisely, we came to a conclusion. Yeah, there is a underlying principle behind all these conservation laws, but uh, due to a paradox. So basically, what happened in the general theory of relativity, we saw that the energy wasn't conserved, and the scientists at that time took help of a mathematician, I mean author, who came to a conclusion. Yeah, that there's a for every continuous symmetry of the universe, there exists a conserved quantity, which is precisely the physics behind which is precisely the theory behind every conserved quantities. So we can take this like from let's begin from the classical mechanics. We see that nature takes the path of least actions. Basically, if they have to move to one point to the other point, the nature will take the shortest path or the shortest time. So this is known as the principle of least action, and uh, due to this principle of least action, they are developed the symmetry, three kinds of symmetries in classical mechanics. That is the symmetry of translation, rotation, and time, which gave their respective conserved quantities as well. That is, translation gave momentum, angular momentum, and energy. So these are the basically the three conserved quantities that we get in classical mechanics. When we move to the realm of quantum mechanics, we see something. We go through something called gauge theory or gauge symmetry. What is the gauge theory basically? A gauge theory is a theory where there is a mathematical theory where there is involvement of quantum mechanics as well as special theory of relativity, and we arrive at in gauge theory. What we have is basically a set of transformative groups. uh, so when these transformations take place for a quantum field or quantum field, basically, then they remain unchanged with the basic physics that lies behind these quantum fields remains unchanged. So we arrive at a conclusion that the gauge symmetries in quantum mechanics keeps the things unchanged. A very good example here is that of local phase invariance. Um, Local phase invariance symmetry. If we see for general Schrodinger equation, we see that the local phase invariance is not actually invariant. So we introduce the concept of the vector potential to the Schrodinger equation, and the thing that we get is upon introduction of vector potential, uh, the local phase actually becomes invariant, and the conserved quantity for this respect becomes the electric charge. Similarly, we have multiple kinds of uh, when we go to that quantum field, and the quantization of this quantum field like uh, it starts to get quantized, and we see that it generates like particles basically. So uh, for this thing, the kind of particles that are generated are called gauge bosons. So for multiple types of invariances,